So a g'day to all the international visitors from here. So that's how I open most of my talks, and then in some of the countries I've been to recently working on Earth observation stuff, they look at me going, what's he saying? Other Australian colloquialisms will pop out from time to time as well. So if I refer to a wombat or something, I can explain afterwards for those of you that aren't familiar with, some of the Australian terms. Open Data Cube. So I'm going to actually talk about a couple of different things. This is going to be a user-orientated talk. This is what it's like to use some of the larger scale systems, do some large scale processing and so forth. It's not per se about HPC. It's about a change that has occurred in space-based observation of the Earth and the impact that is currently having on how we interact with computing systems of all scales. All right, to process this type of data. CSIRO is the Committee on Earth Observation Satellites. So CSIRO is made up of most of the government-funded space science organisations of the world. So some of those names you will know: NASA, all right, obviously, USGS, the United States Geological Survey is another. A new one here in Australia, the Australian Space Agency, ASA. And yes, every joke I have is made up about that. All right, we're not going there. I got to announce it, and there were some amazing things on Twitter at the time at a meeting I was at. But there's also the European Space Agency, the Japanese Space Agency, JAXA, DLR in Germany. There's a whole range of organisations. So it's quite a large committee. Their job is to coordinate the acquisition of data. And the coordination part is partly to stop rockets and satellites smashing into each other in space, because that would be bad in some circumstances. But it's also to help support global initiatives. So things like the United Nations Sustainable Development Goals. Things like get water where it's needed, get food where it is needed. All right, will there be enough pasture land so that we can convert grass into burgers? Things like that. All right, feed cows if you haven't figured that one out. So there's a lot of things that go on in this space now, and that's changing. All right. And CSIRO, the CSIRO, which I am from, and you heard earlier today that the CSIRO helped invent things like Wi-Fi, which you're all enjoying, is a representative organisation for Australia into that CSIRO committee. And so we have a long history in developing Earth observation algorithms and a long history in not launching satellites. And we're very unusually a member of CSIRO, but we don't actually, well, we didn't own any satellites, which is part of the news. So we can talk about that, and we talk about the Open Data Cube, which is an initiative which is helping us to actually propagate more information about how to make good use of Earth observation information. And I'll talk about our industry hub work and the things we're doing there. So what's really new? What's changed, right? Satellites have been around for a while. We've been beaming down things from Landsat 5, 7 and 8 for quite some time now. You all go onto Google Maps and you look at your imagery and you see your grass growing in your front yard, or not, as the case may be. And we've been doing this for ages. Now, there are some other things that are required to do this. There's not only the satellites in space, but you can see there's some people in the middle of that thing standing in a big white salt lake. That's actually in WA, Lake Lefroy. I'm not sure which way east is from here, because I can't remember which way around this building is, but basically drive 5 hours that way east, and you'll probably drive into it. It's a big patch of salt. They're making on-ground measurements of the spectral response of that salt, so that when a satellite goes whizzing by, and they will do this at the same time the satellite goes by, all right, they've got a ground truth, and then they've got what the satellite can see, and they can calibrate the satellite against what is actually measured on the ground. And this happens all over the world, in all sorts of places, some of which are salt lakes, all right, some of which are actually green grass, some of which are red sand, all right, because of the different spectral characteristics depending on where you are. And so there's quite a lot of ground stuff that happens in order to make the satellites actually work above. And that's just for optical satellites. If you look at radar-based satellites, there's a paddock, several paddocks in fact, up in North Queensland, has these big, they literally look like the corner of a cube. All right, so imagine a cube and slice off a corner, all right? That's literally what they're like. They're big metal things, about this big, and they're radar targets. They're in a known location, they're fixed into bedrock, and you can zap it with your radar from the satellite as it goes whizzing by, and it'll beam up, all right, a nice strong reflection signal, again, calibration purposes, right, so you know where stuff is. And that's been going on for some time. A lot of the satellites you see are launched by very big rockets. They're bus-sized things. They cost $1 billion to put up, until recently. All right? That thing on the right is a satellite. It's 10 centimeters by 10 centimeters by 10 centimeters. It's called a CubeSat. I, personally, using my own income, could launch my own satellite into space. 50 grand. Price of a car. Right? Little CubeSat. Can stick some little leg and see that one's got some solar cells around the outside of it. Whack a small camcorder in it. And look, I'm a space agency. Ba-boom. Just like that. I kid you not, that is how it works. There is an entire industry around these things. You can actually make them bigger because you can put them together like Lego. Right? You just have 10 centimeter by 10 centimeter by 10 centimeter units. Right? So you can put these things up. The reason why they're cheap is somebody is paying for a big rocket to launch a big satellite, but it has lots of space around the outside of it. So the way this works is you pack these things around the outside of the big spaceship, right? Launch the rocket into space, launch the big thing, and as the rocket, what's left of the rocket is falling back down, literally turf all the little CubeSats out. All right? It's legal to litter in space. All right? That's literally what happens. And that's cheap. It's actually very, very cheap to launch these things. And there's a whole industry around them. They're getting quite sophisticated. You might be noticing that thing doesn't have any of those like little rocket exhausts on it. All right? They use gyros to stabilize themselves. Right? They do fall down. They don't stay up forever. They do fall down. Right? They burn up in the atmosphere. You're not going to get hit in the head by one. It's all good. But they're really cheap. This is changing the nature of what you can do, because now you can actually throw up 1,500 of these things and have real-time monitoring of a harbour. All right? Because when one falls over the horizon, the next one's coming up. All right? And you can just do this continuously, right? Just have a whole farms of these things flying through the sky. All right? And so it's changing the nature of the industry. The other thing that's happening is the space agencies putting up the proper scientific instruments that are going up are launching an additional 400 of those things just in the next few years. And all of them are higher resolution in space and time, and for optical satellites in spectra, and for radar satellites, they're higher resolution in space and time for radar responses as well. All of that adds up. That on the left is a graph from 1979 to the red line is 2015. All right? In the total accumulated level 0 satellite data in use by a group like Geoscience Australia and CSIRO over Australia alone. That's how we've been collecting it. So it actually does start in 1979. If you can't see it up there, but there is actually a small blip down there. All right? Now, the scale on the left, which you can barely see, is in half petabyte units. I want you to ignore the scale. The scale does not matter. The scale of petabytes does not matter. A global archive from the European Space Agency is 100 petabytes in size. Yes, it's large data. That does not matter. What matters is that line is now so flippin' steep, the amount of data we've got coming in every day is ridiculous. All right? It is huge. That line puts pressure on the entire process of doing Earth observation, because all the calibration that we do on the ground has to be done better. The ability to get data in, get it calibrated, get it corrected, and getting out the door, all right? That all needs to happen. The big blue bit, or the kind of bluey bit that's sitting on top, is actually Himawari 8. Right, Himawari 8 is a weather satellite. It takes a photo of half the planet at 500 meters resolution every 10 minutes. It's a weather satellite. Right? And if you download the imagery, it's way cool as a desktop wallpaper. It looks great. And if you can get some of the emergency management one, it's it's 6 meter resolution, and it's even faster. I can't remember off the top of my head. It's a couple of minutes. And it looks great doing volcanoes, because it's got thermal bands, right? So you watch the plume go up. It's awesome. So this is changing the nature of how we have to deal with it. On the right, of course, there's new opportunities that come with this. You've got CubeSats, you've got launch your own satellite type stuff going on, you've got new sensors coming out, they're much higher resolution, you're collecting things faster. Surely that means you can do something with it, which means you can make a ton of money. All right? On top of that, sorry, is that a question?
That data rate of the emergency, that means you could track wildfires in virtual real time.
Yes. And indeed, there is an application for doing exactly that. That's exactly what it's used for. Volcanoes are less often. Wildfires and typhoons and things like that they use it for. So we've got new opportunities coming here, but the expectations of users also change. So there's money to be made, that's nice. But there's also expectations for users that are changing here, all right? When you pick up your phone and you go to use Google Maps, you are using Earth observation. Your expectation as a user is that when you go to look at your house in a street, it should include the new solar panels you just put on your roof, right? You're expecting that. And if it doesn't have that, you're going, why aren't they there? All right? Moreover, and probably more importantly and harder to achieve, you want to make sure that when you type into the GPS system that you want to go from A to B, that the road that you're being told to drive on actually exists. And the map that you've got lines up with the imagery that is from the satellite. And all of that should be current today. Right? Things to remember. The continents are moving. All right? Over that time period, Australia has moved meters. All right? That all has to be corrected. All right? So you've got to get the colour corrected, you've got to get all the surface reflected. This is just imagery. All right? You've got to move the ground to line everything up with that. Then you've got to make sure that the roads get transported into the actual map so that the navigation system actually knows that you're actually travelling on a GPS track on this map. Meanwhile, your GPS system's also trying to correct itself because the world's moving. We live on Jello. All right? You're getting the idea that there's a lot of stuff that has to happen. For him or RE8, for using that data sets, that's all got to happen in 10 minutes because the next image is coming in. Right, if you're terrified at the amount of computing that's going on, you've only got half of what's going through the heads of the poor people running the space agencies. All right? This is what they're trying to deal with. So CSIRO helps out with this issue for Australia and helps out internationally. We work to do things like securing the Earth observation data supply for Australia. So one of the issues you have with all of this lovely new data coming through is it is becoming technically impossible for a CSIRO scientist to download the data as it's coming off the satellites. There ain't enough bandwidth available for all of you to do it individually, all right? So we have to actually change the way in which we get the data, all right? So we work on that. We have a thing called the Australian Regional Copernicus Data Hub for doing that. We need an analytics platform, which is where the Open Data Cube comes in, all right? We need an actual new approach to the way in which we do our analytics because we don't want to have all of our Earth observation scientists who are scientists actually have to be computer scientists and parallel programmers and using MPI. Most of them glaze over when you do that. All right? So it's like if I came up here and talked to you about algal bloom modelling and how you actually use spectral frequencies to detect cytoplankton. Most of you just glaze over, right? So it's the opposite way around. All right? And we have a CSIRO data cube using this. We're also looking at industry innovation. All right? There's no point in having all these things if you can't actually use them. All right? To make some money and benefit the economy or benefit society. Right? So we do that as well. And we are also, more recently, getting into satellites and sensors. And that's actually a model of a Novastar satellite, which CSIRO actually owns 10% of. We actually own it and operate it. Right? We can actually point it at stuff that we want to monitor. And it's a radar satellite, so it has a limited duty cycle because radar's active, it uses power. Right? If anybody can come up with a cheap way of getting radar to work, there's money to be made by throwing it into space. All right. So in terms of the data supply, we work with the Australian government, Geoscience Australia and a few other groups to actually collect the data for that region. Any odd shapes in the boundaries should not be read into too deeply for political reasons. There are some places we aren't looking. All right. And we actually have a relationship with the European Space Agency to get their Copernicus satellites down. That's one of the largest changes in the Copernicus satellites. They operate like 15 of the things. Global open data, just collecting data all the time, marine, land, radar, a couple of other things. All right, fantastic system. 20-metre resolution, all over Australia for land stuff. It's great. Fantastic data set. So we work with others to make sure this data gets to an Australian data centre that you can use. It's actually hosted on the NCI. And a portion is also handled on a data centre in Sydney, Amazon. All right. And that's there, you can process it in place. It's great on the NCI because you've got all the other data and stuff as well. And we'll probably be mirroring bits of it over to Pawsey, I expect, for the Pawsey users. Although I haven't had that conversation with Pawsey yet. Somebody's probably having that conversation. The Open Data Cube itself, video play. Video, please play. Could you push the play button? No? Okay, we're going to be miming this. No, there should be a PowerPoint. Are you in the PDF? There's a PowerPoint version. We'll have a minor delay here for the moment. So the Open Data Cube, while he's just pulling up the PowerPoint, rather than the PDF. Yeah, we made sure it was there a minute ago. It's there. It's the same name. We know it's there. We made sure it was there. It was open, actually, on the desktop before. It was open in the PowerPoint was open with it. Can you jump me through to the... Bit too far. Sneak preview. About now you wish you had a funny joke coming to mind, but I don't because I'm tired.
Oh, this is on Kansas.
There we are. And push the button. Right, so this does have a soundtrack, but I turned it off because it's got voiceovers and I've cut it slightly. These are the kind of applications you can do with the Open Data Cube. Right? So we've just got coastal monitoring here, just watching this thing erode. What does the Open Data Cube do? It calibrates, aligns, and deals with all of those lovely things about atmospheric correction and everything else for the entire data set, for the Australian version, for all of Australia, the entire continent. All right? And from that, you can do things like land cover changing. This is the vegetation, soil, dirt, bare earth coloured in. And we've been able to connect this thing up to a variety of web services. This one's just running in a web browser. It has a data cube behind it. You can select your products, and it's running a water algorithm. Right? So just detecting water. Right? Which is, if you're detecting water, you're detecting floods, or the potential for floods. So if you analyse a 20-year archive of water presence, you will get a flood risk map of Australia. Right? Now to do that, you have to remove all the clouds and everything else. There's a fair bit of computation involved. Soil moisture, sea ice concentration, this is just examples of things you can do from space. Right? Rainfall monitoring, pastures growing, and so forth, right? So the whole idea of the Open Data Cube is it's both a community and an analytics platform. All right? Its goal is really to promote the use of Earth observation information. All right? Because we have so much of it coming through, and because we have so much more readily available compute capacity, it means that a lot more people can just do stuff. All right? But they can only just do stuff if we can get the data to them, or more likely the algorithms to the data, because the data's quite large. Right? So we need to be able to do that. And we need to be able to present them with calibrated data. Right? They need data that is actually what we refer to as analysis-ready data. Right? Data they can just use. All those corrections that need to be done, all the atmospheric stuff, all the alignment, all the telemetry, all the wobbling in the spacecraft as it went by that affects what it thinks it sees on the ground, lining up all the pixels and stacking them up over time, correcting for continental drift, right? Because 30-year time frame, right? All of that has to be done in advance. And once you've done that, actually doing the math for some of these things is trivial, all right? And HPC users everywhere unite. It's embarrassingly parallel in most cases as well. Right? So you should be able to make it run hellishly fast. Right? And so that's what the Open Data Cube is for. Its vision is to build this community as a starting point. That's its primary goal. It's build this community as a technology stack, open source, freely available, unencumbered. Anybody can play with it. Right? And you can grow it. And we have participants from NASA, USGS, Geoscience Australia, and CSIRO. GA, in fact, started the movement. We joined in with GA on this. The Vietnam Satellite Centre, Space Centre, I should say. UK Catapult is actually a combination of the UK Space Agency and a bunch of industry venture capitalist people, all right, launching stuff. And we have data cubes popping up all over the planet, all right? So I'll come back to that one in a moment. Now, the Open Data Cube really is this simple. Traditionally, what you'd have to do is every individual will have to invest in this value chain. You would have to get the calibration information, you'd have to get the telemetry from the satellite, you'd have to apply your correction algorithms to it, and you would have to do that repeatedly over and over again, and everybody was doing that. Now, if you can imagine you're trying to do a UN Sustainable Development Goal, and you want to compare countries, and they're doing this all individually, all right, you're going to be comparing not apples with oranges, it'll be apples with wombats. There we go, got an Australian colloquialism. All right? Just totally different things, right? You just don't get a global map of pasture lands or whatever you're after, right? So that has been a real issue for just the straight up science goal. It's also a real issue because it's just damned expensive doing this. In some cases, you cannot actually get the telemetry because it's not released, all right? So what we do with the data cube is we provide, within the context of the data cube, the ability to get that data as analysis ready. Right, so we're actually doing things like we're getting the USGS to place their algorithm in a place that I can, on demand, get their surface reflectance product as analysis ready for me, all right, for anywhere on the planet, preferably on demand, because that way they don't have to store two copies of the data, the raw data and the surface reflectance version, which would be 200 petabytes of data. All right, so this kind of ability to change the value chain is part of what we're talking about here. In terms of the capabilities, analysis-ready data is probably the key one, ARD. Getting that working for a lot more people across the entire value chain is what the CEOS activity is really about. That's what we're doing in the back end to really help that work. We want stuff to be ready to run. We want the data where the compute is. USGS are moving their satellite archive from being a file download activity to one where the data is simply available in the cloud, plural. All right? So that you can have the data right where some of the compute is. All right? That's part of what they're trying to do. They're also trying to make it possible for you to actually pull it from the cloud using those high bandwidth networks into a place like Pawsey. All right? Without somebody being charged inordinate amounts of money for doing that transfer. All right? So there's a bunch of things like that going on across the system. We're dealing with pixels, not files. There's a paradigm shift. In the API itself, it's not about downloading files, it's about selecting the pixels you're interested in. So some things I learned that I didn't know about before I started. The way Landsat works, you get scenes of data. All right? So it's a patch of Earth. And one of their metadata filters they use for actually working out whether or not you want to use that scene is the percentage of cloud on that scene. All right? Now, if it's 80% cloud, but the 20% is over the paddock, 20% of the clear is over the paddock I am interested in, that's actually no cloud. But you would have no way of doing that using the traditional methods for doing this. Now, in a world where I can actually compute this on the fly, I can send the request for the patch that I'm interested in, and if it's clear of cloud, grab it, regardless of what the rest of the thing is doing. So there's some paradigm shifts in the way in which we're dealing with discovery and access to this data. One of them is pixels, not files. Right? The ability to integrate across data types, interactive analysis is now much more viable. And when I talk about interactive analysis, I'm talking about interactive analysis for an entire continent. Right? When GA first did their flood risk map for Australia, it was taking days to run the processing. Right? So whole of Australia, 30-metre resolution for 30 years, work out what's covered in water, what's not cloud, right? Remove all the clouds, 30 metres of water, blah, 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 and work out if the water has been sitting there for longer than 5 days, in which case it's considered to be wet. Right? That type of thing. Right? Do that over and over and over again. Now, the trouble is, first time you run it, you discover things like there's cloud everywhere. And your cloud detection algorithm doesn't work so well. So there's patchy cloud all over your map. You also discovered the 2006 tsunami that destroyed the East Coast, drowned Sydney completely. All right? Did anybody here know that there was a 2006 tsunami that destroyed Sydney? All right? And most of the East Coast of Australia? That's what happens when your ground control point corrections all move left. Several kilometres. And then suddenly move back. It wasn't actually that the Sydney got drowned by the water, it was that Sydney actually moved. And where it was now wet. These and other things you find in the data when you actually... Apparently we have 2 Murray rivers. Right? They look oddly the same, but they're next to each other. Right? So there's a few odd things you find in data quality. They're now down to a few hours processing this. It used to be days, now it's hours. The beauty of having a few hours, it means every time you find one of these things, you can rerun it and you can fix your algorithm and you can correct stuff. Scientific method gets faster. Very cool stuff. Now I'm going to run out of time because I'm telling too many stories. But that's all right. Simple data structures are involved. So this is a bit for the geeks of you. How does it work underneath? Simple data structures. We dice and stack the data up and we place it onto the storage system. I'll come back to that in a moment. Place it onto the storage system in those dice and chunked versions, right? Standard, we're going to do parallel file I/O at some point. We're going to be spreading it out to multiple nodes. We want to make sure the I/O is nicely done, right? It's all lined up over time. And we calibrate it all. The standard's called card4L because that's easy to say, all right? So that we've got one at the moment, calibrated analysis ready data for land. All right, that's what that stands for. And we'll do marine, we'll do inland water, we'll do water in the ocean, and so forth over time. It's powered by Python. It's great because you use ND arrays for your access, you use Xarray for labels, NumPy for math, scikit-learn for AI, and off you go. Very, very nice paradigm to work with, particularly for the AI guys. It's the usual things you would expect to find. There's task execution, there's storage management, there's indexing. We index a lot of the files rather than actually going out to the files for the metadata, simply because opening all of the files is a pain in the rear. It just takes time unnecessarily. We know where everything is that way. And we have a way of getting data into these systems and so forth. The data cube itself is only really the middle layer, not the applications area. We leave that to people who write applications. In terms of platforms where we run this in Australia, we run it on the NCI. I know there was a colleague of mine working on running it on Pawsey. Does anybody from Pawsey know if it's actually running on Pawsey yet? No? Okay. Don't think it's running yet. Yeah, I know a colleague of mine was keen to make it run on Pawsey, and we were looking at using the is it Shifter, the Docker thing? Yeah, it was mentioned earlier to help do that, so I watched that talk with interest for that reason. We have, my team actually has a version of this running on Amazon. CEOS head office, the NASA guys run one on Amazon as well. Theirs is slightly different in that they're only using single EC2 instances. They're kind of demo cubes. We're actually scalable on ours, so continental. Right? We have enough, like the entire land vegetation use area for Australia up there. It's all open source, it's on GitHub. We use Docker for a couple of these, and I'm looking forward to seeing how we go with Shifter into that environment on Pawsey, because you've got it there down the track. Storage formats, we can handle pretty much all the things you would expect to handle that are handled by GDAL. We use a lot of NetCDF in the back end, and on the cloud systems, because they're object storage systems, we use cloud optimized GeoTIFFs, which is just to do with the way the internal chunking is done on the GeoTIFFs and the way the headers are set up. There's a kind of a standardization occurring just to make that a little bit more consistent, a little bit more performance. Or in CSIRO's case, we'd actually just do away with files and metadata completely. We have binary arrays sitting there that are indexed by the indexing system. And we actually get slightly better performance because of that. I'm still deciding whether or not the slightly better performance is a worthwhile exercise in that particular case, because people like Amazon keep making things go faster, so the margins are getting less every time we do something. So we're not quite sure, but it was an interesting experiment, and we got a paper out of it. And that's how that works. Again, it's just about rather than internally chunking a file and placing a file as an object, just put the chunks as the object and do away with all the metadata. Stick all the metadata in an index, and then you can pre-plan all of your processing right up front. Not rocket science, although it does involve rockets. We have an execution engine on the cloud as well, which can make use of things like EC2 spot instances. NOAA actually did this, NOAA, N-O-A-A, the US department. They were using this for their global water quality processing system. And they were getting really cheap. They loved it. They kept on doing it, and they kept on doing it. They kept on increasing their processing. And then they discovered one day that the actual price on the spot market, which is a bidding system to get access to the free compute time, was actually completely influenced at that stage on that data center by their processing. So they were making it more expensive for themselves. So trick, used more than one data center. The surprising thing about Open Data Cube, some of you are probably saying, Open Data Cube sounds a little bit like Google Earth, except for it's multi-platform, right? And you have control of your own destiny. And you'd be right. You can actually do global processing with the Open Data Cube if you wanted to. And it is a lot like Google Earth Engine. What is interesting is the confluence of events, the ability to have control of my own destiny, the direct connection to the CEOS data sources and the cleanup that we're causing to the overall flow of the information through the entire system, and the simplicity of you being able to use Python and so forth, are all adding up to a hype curve that is currently well beyond the capabilities of the Open Data Cube, which is not a bad place to be till you come off the other side. But at the moment, it's an interesting ride. So we actually have, this is from 2017, it's almost doubled since then, the number of organisations worldwide that are deploying stuff, particularly developing countries. Right? Again, into response to things like UN SDGs. So there's a bit of momentum behind this thing which really surprised us. We didn't expect that to happen. All right? But it's been great because we wanted to promote EO, and in that sense we've been successful just a hell of a lot faster than we expected. All right? So that's worked really well. We get new applications all the time. This is a global rangeland pastures. This is feeding cows. Right? Pastures, feed cows, convert to burgers, feed the planet. That's what that is. All right? But we also have water quality, we have vegetation, we have landslides, we have, somebody mentioned fires before as well, coastal change, Great Barrier Reef monitoring. There's all sorts of applications that go on in this space around ecosystems. So there's new applications coming all the time. And there's new opportunities. There's stuff we haven't even started to look at. The use of the higher resolution mixed sensors, satellite radar, along with multispectral, along with hyperspectral. Hyperspectral has more spectral bands. You can detect things like mineral anomalies with hyperspectral. So for exploring ground, for looking for new mines, neat ideas there. But there's also things like, there's a whole pile of stuff that sits in the atmosphere between space and the ground. There's UAVs, there's airborne works, there's balloons that can be targeted and moved around to monitor stockpiles or follow trains or chase people. All right? There's all sorts of things you can do with some of these other data feeds that are coming through, and that's where we see the Open Data Cube going next. It's how do I connect this data to that other piece of data, and so forth. And we have an industry hub that we're working on to help engage with industry and help bring these applications to market as well as part of a technology transfer. So we're starting to make that available, put some of our science out there for people to play with, get a feel for, and come up with new business models and new business innovations that they can do as well. So that's the Open Data Cube in a nutshell. It is pretty exciting. I think the change in the way space is utilised, Earth or satellite observations and so forth are utilised, that change in that dynamics is a real burgeoning opportunity. All right? And having a platform where you can go from a laptop with a CubeSat through cloud to supercomputer is pretty cool. There are some other interesting things and opportunities in space as well. One of them is to put the data centre in orbit, because you can imagine if you're collecting 20 centimetre resolution data, which is entirely done, right? They don't currently do that for the whole planet. You actually target it. The only reason why it's not done for the whole planet is because you can't get the data down fast enough, right? So we need faster links down. Or you stick the machine learning supercomputer in space, all right? Now, I met a guy that was talking about doing this. He works in AI. He's an ex-Navy SEAL. He wants to put the AI in space to process the data. What could possibly go wrong? And I'll leave it there. Thank you.